Good morning, everyone. Hi, my name is Owen Naughton, lecturer in Environmental Engineering in IT Carlow. First, I'd just like to thank IAH Ireland, Damien and Paul for organising this course and asking me to give you a brief talk on hydrometeorological data, specifically rainfall and evapotranspiration from a hydrology point of view. So to start, I'll just give an overview of what I'll cover. So first, I'll very briefly cover point rainfall measurement before moving on to the main rainfall datasets available in Ireland. I'll then introduce some simple techniques for checking the consistency of rainfall data, so are there likely errors and gap filling, before introducing some of the main analysis techniques such as calculating areal rainfall, depth duration frequency, SPI and API. That'll be the bulk of the talk. I'll also briefly cover evapotranspiration. I know Clara is talking about measurement of this next, so I won't go into too much detail. I'll focus on the main calculation method, which is FAO Penman-Monteith, and then how you calculate actual evapotranspiration using the soil moisture deficit and what data sets are available. So to start, one of the main aims of hydrology is to quantify and understand the various components of the hydrological cycle and how they interact. And of all those components, rainfall is typically the most commonly measured and often has the longest available records. While measuring rainfall might seem conceptually straightforward, in practice it's not physically possible to catch all the rainfall over a catchment. So the rainfall can only be sampled by rain gauges, which represent a very small proportion of the catchment area, and these values are then extrapolated out. There's two main types. The first are storage rain gauges. This is where rainfall accumulates in the gauge and is periodically emptied, say daily, weekly or monthly. And the amount that's recorded over that period the amount that's stored over that period is recorded. In Ireland, say daily rainfall gauges, they're measured at 9 o'clock in the morning, so that value is assigned to the previous day, the previous date. The other type, which you might be familiar with, are recording rain gauges. The most common would be, say, tipping bucket rain gauges. This is where there's an angular bucket that catches a fixed amount of water, and whenever it's full it tips, and that tip is recorded. So it gives you a time series of rainfall data. There are also other types such as weighing, optical or acoustic, which use various other technologies to do the same thing. There are also, say in terms of rainfall measurement, radar can also be used to detect the spatial extent and relative intensity of rainfall measurements. They have to be calibrated against ground level rain gauges of the type just mentioned, so storage or recording. And you can also use satellite, which I won't really cover, but you can also use satellites to measure rainfall. In terms of siting a rain gauge, so generally if you're doing this on site, there's a couple of things to consider. Firstly, ideally you want relatively level ground, so not on a steep slope. You wouldn't want your rain gauge to be under or overexposed, and the general rule is the distance away from a obstruction should be greater than twice the height. So if you have a tree that's 5 meters high, it should be at least 10 meters away from your rain gauge, as you see in that diagram there, and ideally 4 times the height away. You should also ideally have it at ground level. So you see the second picture that the gauge itself physically modifies airflow. So you can see that as the air is flowing along the ground, it accelerates going over the gauge, which can affect the drop trajectory. So if it's not at ground level, it can actually reduce the amount of rainfall by, for example, 6 to 8% if the rainfall gauge is 300 mil. So ideally, it's something like this bottom picture where the rain gauge is at ground level. So there's some of the physical things you have to take into account. You should also be aware of minimizing instrumental errors like splash out of it. That's related to how big the shape of the orifice and how big it is. Things like evaporation from storage gauges or freezing, that if you're in a climate that's likely to have sub-zero temperatures, you'd want to make sure that, say, there's a heating element in the rain gauge to make sure that it doesn't freeze. Or similarly, if you're measuring snow. Also, operating rain gauges is quite labor intensive. You have to check for leaks, overflows, blockages, prevent vandalism. So it's quite labor intensive. That's why more often than not we would depend on rainfall data collected by Met Air. So Met-Éireann are the main, Met-Éireann, the Irish Meteorological Service, as all of you are well aware, they're the main organisation responsible for the collection of rainfall data. There's three main categories of data sets that they have available. The best quality are synoptic stations. So these would record at sub-hourly time steps, and they'd have a whole range of meteorological parameters above and beyond rainfall. So things like air temperature, humidity, wind speed, direction, atmospheric pressure, even soil temperature, and so on. So these would be the best available data sets. And from those, they calculate estimates for, say, open water evaporation, reference or potential evapotranspiration using Penman-Monteith, which I'll mention later. And also, they calculate soil moisture deficits, which I'll also mention later. And there's about 25, you can see the distribution of those. There's about 25 of those available or present across the country. 5 manual, 20 automatic. They provide real-time data. If you're trying to access it yourself, there's normally a lag for download of about a month, I think, for quality purposes. Then below the synoptic, the next best available data will be climate stations. So there's more of those. There's about 70 plus. They record, a lot of those record on sub-daily, but they wouldn't have the same spread of parameters as the synoptic stations. So they measure things like rainfall, temperature. Some record soil and earth temperatures, solar radiation, and so on, but not all. And I think they're automated. And that website, say wow.met.ie, that's, you can get real-time data for those. The most common rainfall stations would be the daily stations, and these are manually taken. So there's 400 plus of these. As I mentioned, a lot of these might be storage gauges, so the measurements are taken once a day. The values are assigned to the previous day. They have the best distribution, but often the data, it takes quite a long time for the data to be available, and often sometimes there can be gaps present in them, just because of the nature of them. A lot of times they're voluntary. So the best quality data available would be synoptic, but as the least distribution, then climatic, then daily. And all these data sources, I'm sure you're all familiar with it already, would be available from the Met-Éireann website. So here's their web portal where you can click, say, hourly, daily, or monthly data and download them. So that's for downloading time series data. So either hourly or daily time series data. If you're interested in more kind of characterizing the rainfall pattern at a site, you might use long-term data. So anybody who's done hydrological studies, you've heard of SAR, standard average annual rainfall. So this is similar, that it's using a baseline period, a 30-year baseline period. 30 years is considered long enough to smooth out year-to-year variations. So you got rainfall is obviously there's a high level of variability day to day, week to week, month to month. So if you're trying to characterize rainfall patterns, you use long-term averages, 30-year averages. The current reference period is 1981 to 2010, or 2010. That's shortly going to be updated to 1991 to 2020. And that's available at 2-kilometer grid resolution there. So you can go there and you can get, for your individual site, you can get putting in the coordinates, you can get what the long-term average rainfall, monthly rainfall, and so on is for the site. There are also limited long-term time series available. For example, the Island of Ireland precipitation series, which has monthly totals for 25 stations going back about 160 years. And that was developed by Met-Éireann and Maynooth, I think. So that's available from their website. There's also a gridded data set. I don't believe it's publicly available, but there is a gridded data set that is an interpolation of synoptic, climatic, and daily rainfall stations. So it's on a 1-kilometer grid, interpolated from observation, and that's iteratively improved. So as, say, the synoptic stations are, in terms of the most recent data, the synoptic stations are available first, so they're added in, and then it's kind of iteratively improved as other data comes in. So it changes. another data set that's available is the MERA data set, which is, so Met Éireann carried out a 35-year regional climate reanalysis for Ireland using the Aladdin Hirlam weather prediction system. So this is at a 2.5 kilometer resolution, and this has far more data available than just rainfall. It has things like pressure, temperature, irradiance, humidity, wind speed, and direction. So they can all be obtained on a 2.5 kilometer grid resolution for Ireland. So a lot of these long-term data time series are more relevant to if you're looking at kind of climatic studies. So long-term water balances or changes in precipitation behavior. So that covers the main data sets available. Now we'll just move on to some of the techniques for checking consistency. So one of the issues with rainfall is that it has a high level of natural variability, and this means that it can be quite difficult to detect inconsistencies or errors in rainfall measurement because they change so rapidly, and there can be a lot of variability. Like you can have very high months with very high rainfall naturally occurring, months with very low rainfall. So it mightn't be easy to identify errors, for example, caused by, say, if a rain gauge has been shifted to a new location. That would obviously have a different rainfall pattern. Or say a change in surroundings, like a new building is built beside the gauge, or say a tree is now overshadowing it, which would cause a rainfall shadow, so there'd be less rainfall collected at the gauge. So the first technique is this idea of double mass curves. So this is kind of similar to what Judith covered yesterday with cumulative discharge curves. It's a technique for checking consistency over time. So basically, to plot a double mass curve, what you do is you plot the accumulative rainfall at say the gauge you're interested in against the accumulated rainfall totals at one or more other gauges. So either a nearby gauge or a series of nearby gauges. And what you're looking for is a change in slope. That while there's say short-term variability in rainfall records, if you look at it over a longer term using cumulative rainfall, there'll typically be a relatively linear pattern or linear relationship between two adjacent rain gauges. So you should get something approximating a straight line. What you're looking for is any significant deviation from that straight line or an obvious break in slope. So you can see here, say slope 1, for the initial period there was this linear relationship, and then at some point that relationship significantly changed. So if you were looking at that, you go, okay, something happened around there and I need to look at it. Double mass curves are relatively simple to do in Excel, so I'll just give you a quick example of how you do it. So the first thing you have to do is calculate cumulative rainfall. So this is just two example rain gauges or rainfall data sets that are relatively nearby. So if I calculate cumulative rainfall for the first gauge, cumulative rainfall for the second gauge, and plot one against the other, what I have there is a double mass curve. So you can see this is a plot of cumulative rainfall. So from that, it appears that the relationship is relatively linear. There's no obvious change in slope, so you could infer that the data set is reasonably reliable. You could also get the relationship between the two. So if we had a trend line, so you can see there that the relationship is relatively stable. There's no major break in slope. And also, say the one gauge has about 10% more rainfall on average than the other, which is something that you can use to I'll show you later. It's something that you can use to fill in missing data. So now just an example of using this in practice to detect an error. So here's an example of some rain gauge or rainfall data we were using recently for some groundwater modeling or flood modeling work. And when we were trying to model it, we were getting inconsistencies in the annual peaks. So we were looking at the rainfall data, and you can see here, this is just a cumulative time series. You can see here that generally they're parallel, but there's a big divergence down here. So when we looked at the double mass curve for this, you can see this kink in the data there. So there's clearly some inconsistency or error in it. And when we looked at it, there was an issue with the rainfall data that for some reason, in October, I think, heavily overestimated rainfall, and then the subsequent months heavily underestimated it. So there was just an error introduced to their data there. Using double mass curve analysis, we could identify that there was an error when it happened, and then we can also correct for it. So how you correct for it, say an example of this, if you had a overshadowing event or something, so from slope 2, it's being overshadowed. If you multiply the data by the ratio of the slopes, you'll correct the data up to the dotted line. So you can retrospectively correct data. Now, if that's assuming that there's a single event. If it's more gradual, it's a little bit more difficult to correct. Another useful technique is if you have missing data. This is something you'll often come across in daily rainfall series from Met Éireann. You might have a missing month or a couple of missing days. The most simple way of filling in those days is using the average of rainfall stations around it. So you look for nearby rainfall stations, get the average of the rainfall at those stations, and use that to fill in your missing data. You do averages if the long time average is within 10% of the station you're interested in. So that's the formula for doing that. If it's outside 10%, then you should really weight it by the relative long-term averages. So basically you just get similar to the trend line I fit, where you had, say, one rain gauge typically has about 10% more rain than the other. Well, then if you were using that to sub in, you'd scale it using that ratio. So you can do that using a single gauge or a number of gauges. So it's a weighted sum of precipitation values. Now I'll just introduce some key concepts for analysing rainfall data. So obviously rainfall is measured at a single point. That's not representative of the rainfall. That's not necessarily representative of the rainfall over the entire catchment. This is related to what duration of rainfall event, like a very short duration, so sub-daily or sub-hourly. A point, if you had a single rain gauge and a large catchment, the values recorded at that point could have serious errors compared to what the total amount of rainfall over the catchment was. So that's where you come into this concept of areal rainfall. So by definition, what we mean by areal rainfall, it's the volume of water falling over a unit area. So it's the meters cubed per meter squared, or millimeters, and it's a extrapolation or interpolation of point rainfall to area. There are a number of ways of calculating this, some very simple ones through to some complex statistical methods. The most simple would be the arithmetic mean. So if you have a catchment and a number of rain gauges in it, you just get the average of them. So if you've, say, 5 rain gauges, 5 time series, you just average those 5 values at each time step to get your areal rainfall. Then there's things like Thiessen polygons. This is where you divide the catchment into area polygons, and each rain gauge represents the area within its polygon. So it's like a weighted average. Isoheital method. This is where it's like rainfall contours. It's the equivalent of topographic contouring, just with rainfall values. And then some more complex methodologies like multi-quadric surfaces. This is like interpolating. It's almost like fitting a polynomial in 3D, that you fit a surface through your rainfall points at each time step. And then some geostatistical, say kriging and co-kriging. You might be familiar with this if you do topographic interpolation, say in GIS. So a lot of these, say multi-quadric and kriging, just with the advance of computer processing and software, that these are much more accessible ways of interpolating and calculating areal rainfall. The next key rainfall analysis technique that I'll introduce relates to analysing the frequency of rainfall events. Now, information on frequency of heavy rainfall is often needed for things like to design hydraulic structures, flood protection or drainage schemes. Now, one issue with frequency analysis for rainfall is that it's somewhat more complex than the analysis of river discharges, because in that case you're only interested in a single variable, say the peak discharge. Whereas with rainfall frequency analysis, you're interested in the magnitude of the rainfall, but also the duration over which it fell, because different durations influence different systems. For example, in groundwater systems, you might have, say, karst groundwater systems. Some systems would react to relatively short duration rainfall events, whereas others would have a longer memory effect. Now, rainfall frequency is described using this idea of a depth duration frequency curve, or DDF curve, where rainfall depth is quantified as a function of duration for a given return period. Now, we'll just go with the key parameters in this. First is depth, which is the amount of rainfall that falls measured in millimeters. Next is duration, so that's the period of time over which that rain fell. So it could be over minutes, hours, or days, depending on what time scale you're interested in. Intensity, which is a combination of depth and duration, so it's depth divided by duration. So it quantifies rain falling in a given time, so it's millimeters per hour, or depth per unit time. And finally, frequency, which is a probability. It's a measure of probability that a given depth of rainfall will occur during a specific period. And the frequency analysis, that's based on statistical analysis of long-term series. So you're looking at the distributions of rainfall events over hourly, daily, and so on. And the DDF curves, they combine these parameters. So they describe rainfall depth as a function of both duration for a given return period. Now, this analysis was carried out by Met Éireann as part of the OPW Flood Studies update, and they produced a DDF model for Ireland, which is a gridded data set of rainfall depths for different durations and return periods. So they analysed all available rainfall data, long-term rainfall data, carried out frequency analysis on it, and the output was a DDF model of 2-kilometre grid resolution, looking at rainfall durations from 15 minutes to 25 days, and for return periods of between 2 and 500 hours, or 500 years, 2 years and 500 years. Now, this data is available on Met Éireann, where you can get, for a given location, you can get a return period table. So it'll have, for different durations of storm, for different return periods, it'll tell you what the depth is. Alternatively, on the OPW HydroNet website or web portal, for an individual location, you can specify, say, the length of the duration you're interested in and the return period. It will give you the depth. It also has the option of giving you a rainfall distribution. So, for example, if you're looking at the 24-hour rainfall event, the OPW HydroNet portal will allow you to redistribute that, say, on an hourly, if you want to get a realistic distribution. So, for example, if there was 50 mil in a day, it's not necessarily evenly distributed over the day. The OPW HydroNet portal allows you to come up with rainfall distributions. And just to show you some examples, so here's an example of a plot. So you have rainfall depth on the y-axis, duration on the x-axis for 3 different return periods. So you can see that depth increases with duration for a given frequency. In terms of intent, this is the same thing, you're just dividing depth by duration. So intensity decreases with duration for a given frequency. So the longer a rainstorm event lasts, the lower the intensity it has. And I'll just briefly introduce 2 other rainfall analysis techniques. The first is standardized precipitation index, which was developed as a drought indicator based solely on rainfall. And it's defined as the number on the y-axis there is the number of standard deviations that the observed cumulative rainfall deviates from the long-term average. So what this means is you compare the cumulative rainfall for a given period, for example, 30 days, 60 days, 12 months, 24 months, with the long-term average rainfall for that period. So, for example, you'd compare the rainfall in December to the rainfall in all previous Decembers and kind of normalize it. So that's what these show, which is a positive value. So positive value means above average, a negative value means below average. So the red shows kind of droughts and the blue shows above average rainfall. The next is the antecedent precipitation index, which is a simple number based solely on rainfall depth. That is an index of the moisture stored within a basin. It's basically a weighted sum of daily rainfall amounts. So you can see on the left, there's a decay constant. So depending on your decay constant, the rainfall is stored for varying amounts of time within the basin. And what this has been used successfully for, this was used in the groundwater flood, predictive groundwater flood mapping with the GSI for modelling karst floods, and also more recently we're looking at using it for modelling borehole records. So you can see there it's reasonably successful at, API is reasonably successful at monitoring water levels in boreholes. So that finishes the rainfall part of the talk. Just to finish up, I'll just briefly go over some evapotranspiration, some of the principles and data. Again, Clara will be going into more detail after, so I won't go into too much detail. But basically, evapotranspiration, it's the sum of evaporation from soils plus transpiration from plants. In theory, if you could measure all the fluxes other than evapotranspiration, you could work it out from changes in soil moisture content. So evapotranspiration would be, say, inputs irrigation plus precipitation minus surface runoff minus deep percolation plus, say, capillary rise from a shallow water table plus or minus changes horizontal flow plus or minus soil water content. But realistically, it's very difficult to quantify all these various parameters. And it's very difficult to measure, which Clara will talk about. So generally what's done is evapotranspiration, reference evapotranspiration is estimated using the FAO Penman-Monteith Equation. This is the equation here. The main thing to know about it is that it's derived based on meteorological data. So you estimate potential evapotranspiration using solar radiation, air temperature, wind speed, and humidity. So by combining those parameters, you get an estimate for reference evapotranspiration. Now, reference, when they say reference, it's for a reference grass crop. So if you see reference or potential evapotranspiration, it's specifically the evapotranspiration from effectively a grass surface that has no water limit. So it has access to as much water as it could possibly use. So it's the maximum rate at which evapotranspiration can occur. Now, there's a number of other techniques for calculating evapotranspiration, so like Thornweight and Hargreaves-Samani, which some are based solely on maximum temperature if there's data limitations, but the gold standard is Penman-Monteith, and that's what's used, say, in Ireland, using synoptic station data to estimate potential evapotranspiration. So just to get an idea as to how evapotranspiration varies in Ireland. So here's an example of seasonal variation. So these are kind of 30-year averages for evapotranspiration. So you can see there's a seasonal, as ET is related to temperature and radiation. So there's a summer-winter gradient that you get higher evapotranspiration during the summer than during the winter when there's more crop growth, temperatures are higher. So it would range from, say, lows of 15 to 20 mil or less than half a mil per day, say, during the winter months, up to monthly values of 80 plus millimeters per month. And it also can vary a lot daily. So this is just a plot of the long-term daily potential evapotranspiration from Dublin Airport. So you can see with the black line, that's the mean. So you can see the seasonal variation. So it peaks in the summer months, but you can also see day to day, there can be a lot of variation. As there's a lot of variation in weather conditions, evapotranspiration can vary a lot day to day. And it's important to understand that that's reference or potential evapotranspiration. That's the maximum rate at which it occurs, or it can occur for that reference crop. Now that can vary depending on the vegetation in the catchment, so it can vary depending on its grassland or peatland or forestry. There's different scaling factors for those. It also depends on water availability. So often the actual amount of evapotranspiration is less than that maximum potential. So if you have a dry period, plants will use up the water, a deficit will build up, water will become harder for plants to access, so the actual evapotranspiration rate will drop below the potential rate. So it will be less than that maximum, less than that potential or reference. So there are two key concepts are actual evapotranspiration, so it's the rate at which it actually occurs, and that's related to, say, the history of So what has happened in the past? Has there been a dry period or a wet period? Is the soil saturated or not? And also the current soil moisture deficit. So, and that's defined as the amount of rain required to bring a dry soil up to field capacity. And depending, if you get involved in say modeling catchments out of rainfall runoff modeling, different models will model, say, soil moisture deficit and recharge and actual evapotranspiration differently. But the simplest one, and the one that's used by Met-Éireann, is the hybrid soil moisture deficit model. So this is where it's assumed that actual ET decreases linearly to zero as the soil moisture deficit approaches a theoretical max of 110 mil. So what this means is if there's no soil moisture deficit, actual ET is the same as the max or potential ET. If the soil moisture deficit is say if the soil moisture deficit is 55 mil, it reduces linearly. So it drops off. And then if the soil moisture deficit is 110 mil, there's no evapotranspiration. So that's just showing you the model. You can find this on the Met-Éireann website. But one advantage of this is it's relatively easy to implement yourself. Like you could implement this in Excel and use it to get an estimate for actual evapotranspiration. And this has been used we've used it quite a lot in, rather than looking at, say, the relationship. If you're trying to get the relationship between groundwater levels and rainfall, it's often worth, say, if you're doing just basic analysis or water balances or cross correlations, it's often worth calculating the soil moisture deficit using this model, calculating actual evapotranspiration, and then getting, say, an estimate of what's left over, and then trying to relate water levels with that. We've used this, say this is built into our groundwater models, and we use this model. In terms of where you get data for evapotranspiration, you can get point estimates. These are based on the Met-Éireann synoptic stations. So these use Penman-Monteith based on meteorological data to calculate time series of a reference of evapotranspiration. You can also get gridded estimates. So I check in an EPA, GSI and EPA funded project, that they used climate models, say Cosmos, WRF, and they took the mirror data. And we looked at calculating evapotranspiration from those climatic models. So the climate models had the data you needed. So it had humidity, temperature, and so on. So we calculated evapotranspiration. So there's gridded, you can get gridded estimates going back, it's about 30 years. And that's available, freely downloadable from iCheck. So that's the end of my talk. Thank you for your attention. And if you have any questions, I'd be happy to answer them at the end of the session.